Thanks everybody for joining. I'll give my talk about a new project and the idea of a new project that we have started recently on the topic of computational AI robot synthesis. So I'm not a person that works on evolutionary robotics predominantly, not at all. I'm one person that works on autonomous systems for flying robots. And it's a well-known thing that the most widely used flying system that you see in the small drone community, the quadrotor, has its design roots in the beginning of the 20th century. So that's 1922 with the Boltzmann helicopter. Now, this design, the same concept, back then manned, now unmanned, is actually the same state-of-the-art concept. In the manned aviation, it never really kicked off as a major idea for many drawbacks of efficiency and so on and so forth. But in the unmanned aviation, became the greatest hit in the small drone community for the last decade, more than a decade now. So it raises the question, is this really the optimal design, or is it just a design that we get for convenience? And the fact of the matter is that even the first papers for quadrotors clearly said that the main benefit of the system is the simplicity of the design. But of course, it is known that it's not by far, it's not the best system when it comes, for example, to efficiency, endurance, a combination of agility and efficiency, and so on and so forth. So it's a good all-around system, but has major compromise in aspects such as endurance versus agility. So if you have an agile system of that class, it can have very bad endurance. And however, due to its major simplicity, it has gained essentially the greatest application diversity. The set of applications it is used is the greatest one in terms of all the other types of unmanned aerial systems. So you can see it, from warehouse management to flying in forest to industrial inspection, open sky, coverage, and so on and so forth, or even in extreme cases such as you see deployments from our side in underground mines and so on and so forth. And this is not to say that these systems are bad. The results you see here are all full autonomous systems that, here we do some previous work together with DARPA, the defense agency in the United States, for exploring underground mines. And the robot is going, carries a bunch of sensors, LiDARs, vision, and so on and so forth, works together with ground systems. And, you can have systems that have very high capabilities. But what is definitely true is that, we overuse one type of flying platform. You can see also rotorcraft that are more or less like helicopters. Most of them eventually represent miniaturizations of manned designs. So things made for manned aviation, miniaturized to the small scale. And you never see a system that really was designed to fit a mission or an application or an environment. And of course, this contradicts the natural paradigm. Now, in robotics, we also have biomimicry. So we do have people, excellent researchers, that try to create designs that mimic nature and therefore make them applicable to the niche environments they may care for. But the paradigm we want to think is, can we just not be attached to nature by any means? Because it's also not true that we have actuators of the same type of nature, or at least we don't have high performance actuators that are like muscles and so on and so forth. So can we just have no hints attached about how we design a system, but equip an algorithm that allows to evolve new candidate body proposals. And each of them gets trained end to end for a navigation policy, not only a dynamic control policy, not only a control methodology for state feedback, which means velocity, position, orientation, and attitude rates for such flying vehicles, but essentially from high exteroceptive sensing like vision, depth sensing, and so on, so high dimensional input, all the way end to motor action, so actuator commands. And see, for a class of environments or a class of applications, what new types of airframes, so new types of vehicles, new flying platforms, in combination with new flying policies, methodologies to allow the system to fly autonomously, trained through data in simulation, will give the best new combination of body and intelligence, body and brain. And the hypothesis, just for the sake of discussion that we're doing, is that if we optimize two systems, one generation optimization for an aircraft that flies under the canopy, so within the forest, within the trees of the forest, or an aircraft that is made to maneuver through large kilometer-wise lengthy tunnels of and networks of underground caves, these two embodiments and their autonomy functionality will be majorly different. And I think you all understand the concept. And indeed, this is a new idea that we have started in the last few months with a set of colleagues that I will mention at the end. But we already know that, of course, if we evolve dynamics, we can have the conventional hexarotor, which is a multi-rotor, much like the quadrotor, but just with 6 propellers, which works very well for most cases, but it's not optimized for one particular type of flight. If we optimize with evolutionary algorithms, for systems that fly predominantly forward with limited need to go back and forth all the time, mostly in one direction and left and right. We get different designs, such as the one you see in the middle. And of course, we also do know that nowadays we do have the capability to scale, to train navigation policies end to end in a scalable manner. So here we are trying to create a methodology that allows us to go from depth data, image data, all the way to learn with no prior information a policy to fly an arbitrarily drone, not only a quadrotor, in less than an hour. And we have this goal of less than an hour so that we can play this evolutionary game of creating a new body, training a policy, see the performance, driving again evolution, learning a new policy in a scalable manner because we need thousands of iterations. And still, it's an expensive process to train with input data being a high dimensional vision sensor, which means roughly 1 million pixels. It remains an expensive process, but we're trying to get it at least this end-to-end process to be less than an hour. And for that, we are exploiting ideas such as using the previous controllers, previous policies to bootstrap the learning of a new policy, and so on and so forth. I just want to show now some basic ideas how this can happen in a modular manner, which we have identified this to be the key computational bottleneck of this process I'm planning. So the key idea that we're proposing is that you are not learning really an end-to-end policy without structure. So you don't just let the neural network to learn the policy on its own, but you break down the neural policy. First of all, you question what you need to maintain as information as little as possible from depth sensing. And essentially, we are creating what we call the collision image, which, long story short, encodes the simplified information necessary to avoid the obstacles in your vicinity. So any gap that is smaller than the robot size, it's diminished, doesn't have to be retained, and so on and so forth. If the robot doesn't fit, this information is unnecessary. So we reduce the input dimensionality first. We train a neural net that encodes in a very low dimensional space. It looks like an autoencoder. It's not really an autoencoder because it's not learning to encode the input image. It's learning to map to the new collision image set and encode this in a very low dimensionality. So we go from 1 million pixels in the input to roughly 64 variables, 64 floats in the latent space. Then we get this pre-trained latent space, and we feed this compressed latent. We feed this alongside basic state feedback, like orientation and attitude rates, which are cheap to get, seamless to get with an IMU. Any IMU will give you this with reasonable accuracy. And then we train with reinforcement learning, a policy to learn how to fly. No need to discuss here the particular reward function, but essentially it relates to the ability of the system to avoid the obstacles in its vicinity. So have zero, or essentially aiming for zero crash ratio while reaching the destinations. Destinations being waypoints in simulation, in training, having privileged information for position. In inference, not having this privileged information, but inferring this implicitly through the depth and visual sensing of the system. And then we use, of course, highly parallelized simulator. I also mentioned something about the open source release of the simulator, not only for multi-rotor platforms of the conventional class, but also for arbitrary multi-rotors, such as those I highlighted in the beginning. We use asynchronous PPO, so proximal pulse optimization, that is fed with this compressed latent that has been pre-trained. This compressed latent is sensor specific, not flying dynamics specific, which means we just need to train once. We don't need to retrain all the other times for the robot. So we only train from the latent space forward to the navigation policy. We get this, we fill different environments with different densities of obstacles and so on and so forth, and we have a curriculum about how to learn more complex cases. I'll just show an example of this, how it works in practice. Eventually, now this is going to be with a conventional quadrotor because we still have simulation work for evolving new airframes and experimental work for learning these policies in this modular manner, which allows us to train relatively fast. This used to be a multi-day learning process. Now it's a process that it won't take too much on any reasonable 2 GPU system. And of course, this is still inferior what you can get with model-based design and mapping and so on and so forth. But these are all policies that have no map information. It's using no global information for the environment. It doesn't even try to reconstruct any global information. It's purely a policy based on the immediate sensing observation the robot gets now. So this depth image that you see, which you can get from a stereo camera, you can get from active stereo, like in this particular case, and so on and so forth. And the whole idea is that we don't need to give specific algorithms to the robot. We literally can just go end to end with a caveat that we're actually breaking down the neural net into different neural nets, that some of them are pre-trained because what they represent, which is how the sensor information is encoded is not platform specific. Even if you change the position of the sensor, it doesn't matter. So yes, as long as you use 3 or 4 known classes of sensors, you can have this pre-trained, and then you only train the dynamic aspect of it and how this latent space is exploited by dynamics to ensure safety. So the last thing I want to highlight technically is that the most key computational component for this is the simulator that supports arbitrary configurations. And this is where I want to spend an extra second, which we have open source in its latest release right now. And through this open source, we believe we can support new members of the community to build in this direction. So now we give on this latest open source release, which we did 2 days ago, not only we allow that you get arbitrary airframes like that, but we also have vanilla controllers and policies trained, or policies that you can train for these arbitrary airframes, which means many people can just go at least on the dynamic side. And we are open sourcing slowly also the work that relates to using depth sensing to fly autonomously and so on and so forth. So that, I don't want to say anything more. The project that I referred to in the beginning, which is in its very early stages, we started last November, contains the partners that you see here. Some of them are actually other organizers today, like Arin and Gusti, and so on and so forth, but also many other partners, which I want to give credit for being involved in this effort, and with which we hope we will be able to give you much more impressive results in this direction very soon. With that, thank you. Nothing else from my side.